All right. Hey everyone, welcome again to my stream. Um, so, so today I'd like to do a few different things. One thing I decided to do was put together a little agenda. So these are some items that I would like to try and do this stream. Not sure if I'd get through it all, but we'll see. So let's go over a little bit of what I've got here. So first thing I'd like to do is to go over some changes I made since last stream. I actually kept working on the emulator since last stream, and I'd like to go quickly over some of those changes. I'd also like to talk about the bug that we had that I was working on last stream, which is basically this weird address range access. I was thinking of implementing some features in the debugger to actually help me debug this bug. So one of them is the ability to be able to step and give a certain number of instructions that I want to step. It's an optional parameter to the step instruction. This would really help me because I can figure out how far I would like to step ahead, and then from there turn on the trace and actually trace from there. And also I'd like to add the ability to add watches in the debugger. So watch, this is a read watch, and this is a all watch, I believe it stands for. So basically both read and write. So this is a write watch on an address, read watch on an address, and read and write watch. And the ability to list all the watch points. So this is a feature that's also known as data breakpoints or hardware breakpoints. So I'd like to implement that. And once I have all that, then I'd like to keep debugging the weird address range access. So yeah, that's basically what I want to do. So let's start by going over some of the changes I made since last stream. All right, so let's open up here. I think maybe it's easier if I do it on GitHub. Okay, so Vectrexy, commits. I'm not going to go over all of them. I just want to kind of highlight a few of the ones that I think were interesting. So, okay, so first one is this one here. So replace cout with printf. So yeah, this is kind of to address that I had some performance issues with the trace output. And I took some time since last stream to do some to look at some profiles of what was going on when I actually ran with a trace. And yeah, it was very interesting, very informative. What I learned was what I already knew, but was confirmed, is that cout is a lot slower than printf. So mainly it just consisted of replacing lines where I was using cout with printf, which made a lot of sense, especially on lines where I was actually calling my formatted string helper class that already took printf style strings and then would return a temporary pointer to the string to cout. Now I just literally printf that directly. And this actually gave a nice speed increase. It's actually, significant. Cout can be extremely slow. So that's basically this change here, and you can see kind of it's all the same. All the couts are replaced with printf, and of course it changes some alignment stuff, so that's why it just seems like there's more than that, but really that's the only change you really see here. And you can see it in the dark, what's darkened here. So yeah, that's one change. Sorry, where was I? Up here. So that's replace cout with printf. Actually, one I did before that was to improve memory bus performance by using a sorted vector instead of a map. So yeah, this basically boils down to how memory lookup is done. So anytime the CPU or any chip, right now it's just a CPU, but eventually it probably will be the VIA chip, needs to do a read for an address or write to an address. It does that via the memory bus class. And the way the memory bus works is that we have different devices that connect to the memory bus initially. And so what I was doing was I was keeping a map, I think we can see it down here, a map of a range of memory to a device info structure, which stores basically a device and the memory range. And I had written this to do here, replace with vector of device info and just use linear searches, and that's exactly what I did. So it became, instead of a map, it's now just a vector of device info. And this vector is actually sorted by address. So we can see here when we connect a device, rather than just in place a pair of range and device info into the map, I just push back this new device info for the device, and then I sort, sorting by taking the first address in the memory range. So what that lets me do is it lets me speed up this find device info function rather than iterate through all the map entries looking for if the address is within range. I'm able to just first of all make sure that the address is greater than the very first device's address, is greater than the first device's initial address. And then after that, I just look for the one whose address is less than the end of the range of that device. So if they're all sorted, this is much faster. It actually was a significant performance boost for me. So yeah, so there's that. What else? Okay, not so interesting here. Oh yeah, so another thing that I found was that the coloring of the output, although really nice and helpful when reading the trace output, was also causing a slowdown. Now, not in the fact that it was coloring. What it really was is that it ties down to buffered output. So what this change says is add toggle for color that when disabled also enables much faster buffered console output. So what I played with was the ability to modify the buffer size for std out using set vbuff here. And what I was able to do is I was able to say, in this case, what I wanted to do was be able to set 100K buffer for buffering output, which actually is a significantly faster way to do the trace. The problem was that when I did this, it broke the coloring of the output. So I'm not exactly sure why, but it looks like what would happen is I would set the color, and what I suspect was happening is like one of the colors would be used for the entire buffered output. But when I do line-based, it totally works. So what I decided to do was, if you enable coloring, then I go back to to disabling the buffering, which is what it is by default on Windows anyway. And in that case, the coloring works fine. But if you disable coloring, then I enabled a much faster 100K buffer. So in fact, I can even show what that looks like. So if I run my debugger here, and also by default, I disabled the coloring. So to turn on color, I just type color, and it says here color enabled. And so if I continue, it goes like this. And if I turn off the coloring and I continue, it goes a lot faster. I mean, I don't know if that's obvious here. I just want to set this register so it actually does something. Oh, sorry. I actually turned off the trace. Let me try that one more time. Okay. I'll actually start by setting the dude register. Okay, so with coloring enabled, it does this. With coloring disabled, it gives me a crash somehow. What happened here? Vector subscript out of range? That's super weird. Okay, let's try that again. Just want to see. It seems related to actually disabling the coloring. If I just continue like this. Wow. Why would that happen? Okay, yeah, there's some weird bug going on here. Because if I do the same thing, but set coloring on, oh, okay. No, it's the same thing that happens in both cases. It's just that I get this assertion during the time where it's outputting to the buffered output, but it hasn't actually flushed it yet. So that's why we didn't see anything. So there is something here going on where it's doing a load X, and I don't know if this is actually because of the load X. No, it's probably not. It's probably the next instruction. And it's now trying to read out of address 1, which isn't valid. And so this is interesting. This is okay. I'll get back on this. This is related to another change that I made. So it's very interesting. Okay, so let's just keep going. So this is the change to disable the colored output by default, which, like I said, really speeds up significantly the output when the trace is on, which is useful. So that's not interesting. Okay, so this is actually what is related to the assertion we're seeing now. So this says allow launching without ROM, in which case it will load Mindstorm. So this is the last change I want to go over that I did since last time. So up until now, the way Vectrexy would work is you'd have to pass it a ROM as input. Now, I did that because I was just thinking, you know, like any emulator, we need to load a ROM, and I required it. But in fact, as I've said many times, the Vectrex doesn't require a ROM, doesn't require a cartridge, basically. If there's no cartridge, it'll load its internal game, which is Mindstorm. And in fact, I have this code to load the ROM, but I have yet to hook it up in such a way so that it goes to the ROM when that it goes to the ROM when it detects that it's there. I haven't actually figured out yet how to even do that. There must be something I need to set somewhere for that to happen. So for now, I mean, I'm not really interested in actually, by having forced myself to load a ROM, what I was doing was I was hiding some bugs. Bugs that would occur where some instruction would try to access memory in the cartridge space, like what's happening right now. So the cartridge space is the first 32K in the memory map. Oops, sorry about that. In the memory map here, the cartridge ROM space ranges from 0 to 7 FFFF, which is basically the first 32K of the address space. And well, what I was doing is I would load a cartridge, and based on the size of the cartridge, I would just allocate a buffer from like 0 to whatever the size of the cart was. So like some carts are 4K. So anything from 0 to 4K would be some allocated piece of memory. And if anything accessed that range, I got no errors, nothing, even though it's unlikely to be valid since I'm loading Mindstorm, and Mindstorm is in the range down here. So from E000 to FFFF. And if Mindstorm or the BIOS make any accesses in the cartridge range, that seems wrong, right? I wasn't detecting those from, say, 0 to size of cart, but anything outside of that range I was detecting. So, all that said, it looks like even right now, with very, very early on, I'm getting an access here after this instruction that is trying to read at address 1, which seems a little off. This effective address here ended up being 1 for, let me see if I can figure out what the instruction is here. So print op, simple template, it would have to be in here, disassemble operation. I've probably already built this instruction here. So there we go, load effective address, load LEAX. Let me just drag this here. Clean up a little bit of my watches here. Okay. So it's a load effective address into X. Okay. And basically it's an indexed mode instruction. So we were in the process of disassembling the indexed instruction. Okay, so it actually looks like this. A load effective address x1, comma x. And so then the question is, I'm guessing x is 0. Sorry, where can I see that? CPU instruction. No, sorry. It's what I'm looking for actually is the registers. So yeah, x is 0. So that's a bit strange. Or not. See, okay, so we can see right before there, it's saying load the value at C825. Load the value at C825 into X. Now the value at C825 happens to be 0. Now, is that wrong? And that is a good question. So C825, if we look at the memory map, C825 falls into this range, C800 to C87F, which, as I remarked here, these are ranges that are used by BIOS for housekeeping. Now, it's very, you know what? You know what? I would not be surprised if this might be the way the BIOS checks to know if a cartridge has been connected. This actually might be the way that the BIOS checks. And in fact, one way we can figure that out is, let me do something. Because I have all the BIOS routines here. Normally when I load up my debugger, let me just try to find, where is it? Yeah, I always start off by doing this load symbols, vectrex.inc, which loads up symbols in this file here that help me to figure out what functions we're calling in the BIOS. So let's do that. Let's also set this, and we can leave the trace on, that's fine. Okay, so let's try this again and let's take a look. This is very interesting. Okay. Actually, what I need to do is I need to do that, and I'll turn on coloring so that when it does crash, we can take a look at the trace. What I'm realizing is I need to probably try to handle these kinds of assertions that I'm getting and make sure to dump whatever's been buffered. But anyway, so here we are. Where are we? Wait recal. So actually we're in the wait recalibrates. So this is completely unrelated. So let's go see what wait recalibrate is doing. So this is the BIOS routine that's being executed. So I remember this one is meant to wait. So let's see what it says here. Wait for T2, the refresh timer, to time out. Then restart it using the value in C8-3D. Okay, that's not what we're reading here, is it? Vector loop count. No, okay, that's fine. interesting, unless I'm just thinking about load effective address X and what that means with an indexed LEAX. It was LEAX 1X that we saw right here actually. So okay, so this says load into X the vec loop count. Now the vec loop count is stored in this word here, and as we saw, it starts off as 0. Then we say load effective address into X 1, X. So, you know, maybe the way I'm doing LEAX is incorrect. I'm wondering if that's what's wrong here. It's possible. Let's take a look here. I have, oh, I must have closed it accidentally. Oh no, okay, I have it here on my other screen. Load effective address. Form the effective address to data using the memory addressing mode. Load that address, not the data itself, into the pointer register. Okay, so I'm wondering if the problem is here. I'm forming the effective address, and then I'm going to read it. That's it. Okay, this is more of a problem with just, okay, this is a disassembly problem. The fact that I want to disassemble this instruction, and I'm trying to read at, like I want to read what's at this effective address, but in fact the CPU won't be doing this. The CPU will just take this value, this effective address that got formed, and store it into X. But my debugger is trying to read, and then that's causing an assertion, which is unfortunate and interesting. I'm trying to think what I should do here. It's kind of like what I want here is I don't want the error. Like I don't want this assertion to occur if it's the debugger that's trying to display what might be there. Or maybe what really should happen is that the debugger shouldn't be trying to read there in this specific case. It's hard to know. What's the right thing to do? I wasn't getting this before because I was loading a cartridge, and of course, the cartridge I was loading was 4K in size, so I was just reading some value out of the cartridge, and it didn't matter for the debugger, and then the CPU didn't care. So now that I don't have a cartridge, I'm getting an out of bounds access here because my data is actually, see in the cartridge, M data here, which is a vector, has not been allocated. It's got size 0. So anything I try to read in there is going to have this assertion occur. Like here, vector subscript out of range. What to do? What to do? There are different options I'm thinking here. I'm thinking about options whereby rather than read directly from the memory bus, I have some kind of like, I just use a function that that my debugger would use to read from the bus that would have some kind of like try catch in there, and any kind of invalid access would throw an exception, and then it would say, oh well, this is just an invalid read for the debugger. Report that, but keep going. Now, if the processor causes an invalid read, then it would assert, and that's okay. But if the debugger does, we don't really care. The only problem I have with that is that I would need to use, in order for this, instead of this asserting, I would need to use the .at function, which would throw if exceptions are enabled. But it's also slower than direct access this way. See, it says here, break when this exception. So this actually is an exception, isn't it? What would happen if I kept going? It's a very good question. Let's try it. Let's say, if I just as a test, I'll put a try catch block around this. Equals 0, equals A. Let's just see. Do I end up, oh, all right, and I'm going to have a problem here because like that. Okay. Does this work? Let's see if this works. Okay, so I get this exception. I hit a 5. Can I continue? Where are we? Unhandled exception in Vectrexy, an invalid parameter is passed to a function that considers invalid parameters fatal. Right, of course, yeah. It's not like a safe kind of assertion. So it won't let me continue. So that means, like if I did this instead, like at, like this, and there's the catch. That is our load effective address. So you see that works. Maybe that's okay for now. Maybe that's okay for now. And then if I hit a 5, see it continues going because the CPU didn't care. Oh, and then I got another one here, again coming from the debugger. And how many memory bus reads? I mean, there are quite a few, aren't there? I mean, some of these, well, any of these could fail. So maybe the trick is to put a little try catch a bit higher up. This is disassemble op. printing the operation. We have a memory bus read right here. Now this one here should not fail because this is actually reading, this is reading the hex instruction itself from the instruction stream. So this one should be fine. But it's stuff like this where we are forming an effective address and then we are reading here. So like we disassemble based on addressing mode. Yeah, not sure what kind of granularity I want here. Do I like fail? I don't want to fail the disassembly of the entire instruction. So maybe for now I'll just start with, I don't know. Okay, here's what I'm thinking. Let me go up here somewhere. Let's say here. Standard string. Try read memory bus read, I don't know, try memory bus read, where we pass it the memory bus, and we pass it an address. We do our try catch here. And the idea is that we do the read, and what we're trying to do is we're trying to return a stringized form of the resulting value. I'm just thinking, it's weird. Is it weird that I'm returning it as a string? And I mean, okay, let me just kind of finish my thought and we'll see what it looks like. So what we want to do is we want to say turn memory bus read like this. Now, and in fact, I need to do that, and I need to put this into a string. So don't I have something to do that here? I don't know. I just want to, what is it again now? I can do standard, it's like I to S or something. It's in C++ 11, int to string. To string. Standard to string, all right. So I say standard to string memory bus read. Otherwise, what I want to do is I want to return a string like invalid, like invalid access something. Or like invalid read. Let's do that. So this is what I mean. So that this way, I can kind of rewrite this code a little bit, where instead of a uint value like this, it'll actually be a string value that I just stick into my comment. So like, let's say we just get rid of this now. So yeah, like, just to make it obvious, I'm storing a string here. Try memory bus read, pass it to memory bus, pass it the effective address. And here, oh yeah, and then there's the problem of returning it as both a hex value and decimal form. Unless what I do, instead of this, I actually do something like similar to what I had in this code. Do the read, and then we do the formatted string. Except it will just look like this. No, sorry, like this. With the value twice. So it'll get converted to an std string. Now if I did that, then I could even shove this in here. Put %s here. Like that. I don't really like the name try memory bus read anymore, but I have a feeling like I would end up using this in multiple spots for this pattern. Every time I need to read one value from memory, I could read it this way. If it works, I end up returning the string in this kind of normal format, because this format actually turns out to, I have this in a few places. Yeah, it's like my common pattern. So, and probably all these places is where I would end up calling that function, because that's really where I end up needing to read a value. Like here, see values memory bus read. So this is a place where I would use that and extend it here. Again, here in direct as another value memory bus read. This also could be replaced. So like, yeah. Again here as well in my print, right? Because even my print could assert, and this would end up, working in that case. So I think the only problem I have with this, I think this works. I'm just not happy with the name. But I guess it's okay for now. If I come up with a better name later, I'll change it. So let's see what this actually would look like. Oh, okay. What's the problem here? All right. This returns a standard string, so therefore my autocomplete stopped working. I hate when that happens. Okay. Let's see, did that work? Okay. So try to run here. And I'll just put a little breakpoint here and say, copy my usual preamble, color. Okay, here we are. So I hit my breakpoint. Trying to go back into debugger here and take break into debugger and set it to true. And this is what it looks like now. Load effective address 1, x, which is 1, 0. Effective address is 1, which is equal to invalid read. Which is fine, because that's just in my comment. And if I actually get an assert from the CPU, I'll even see it here in the comment in the cases where the CPU would actually read from that effective address. So yeah, I think this is pretty good. All right, and now I should be able to continue. And now, just to show you, if I turn off color, you can see how like this is buffered. It goes way faster. And if I break and I actually turn off the trace altogether, this runs even faster. And something that I realized, I think I may have mentioned it last stream. Okay, so we just got another out of range, which I think is the one I was expecting. Let's see. Yeah. So before I talk about that, what I was going to say was that I may have spoken about this last stream. One thing that occurred to me is sometimes I'm running this and I'm waiting for seconds while it's running, and then eventually I get this crash, you know, like whatever is the next crash. And the reason why it takes seconds is because my emulator is already emulating the real timing of the Vectrex CPU. So because of that, you know, it's taking seconds because the intro screen to the Vectrex runs, then it actually shows the Mindstorm screen. I suspect, based on what I've seen from the output, we get as far as like the Mindstorm screen, and then I believe it even gets into the gameplay, because that's where it would render the score at the top. And I'm pretty sure that there's this function, the one for handling the decimal adjustment, that would only be called in the case of showing a score on screen. So this takes approximately like 10 to 12 seconds before we actually get to this area, and that's in real time what's happening with my emulator. All of that to say is it would go a lot faster if I, you know, didn't emulate the real timing. So one thing we can do is kind of like implement some kind of turbo mode. So I might maybe do that today. We'll see. You know, some kind of debugger, or I'll just say turbo mode. All right. Okay, so let's see. Okay, so the crash that this assertion that just happened now, oh, I think I killed it. I'll bring it back. This is actually the problem from last time. So let's just take a look at it. If I run, trace disabled, so see, this is what I mean, where it's going to take about 10 seconds because it's running in real time. Or less, actually, maybe about 5 seconds or something. We get to this point where we have a load instruction that's running, and this load instruction is trying to read from address 0. See here, address 0. Now, that's interesting. See, we're getting actually a break right here in the debugger because I don't have a try-catch around this read. This is coming from the CPU. So this is good. This is what I wanted. Now, it's trying to read at address 0. Last time, we were debugging, it was a similar problem, except that it was a read at this address here, 3409. And the reason why it's now 0 as opposed to 3409 is because now we are no longer loading a cartridge. And previously the cartridge I was loading was 4K. So basically, if you come here, how does this work again? Scientific. So yeah, it was 4K, so 4096. Oh, sorry, I want to stay in programmer. Right, so in decimal, 4096. And you can see that's like, I think it was 4K. Maybe it was, actually, no, let me double check what it was. So I was trying to load ROMs. It was Scramble. Yeah, 4K. So basically, 4K means that from 0 to hex 1000, I don't know if it was inclusive, probably was, you know, -1. So FFFF, in the range of 0 to FFF, any kind of CPU access in there was not a problem. As soon as there was an access above this and up to 32K, I would get an assert, like I would get this thing. So that's the case here. 3409 is out of that range, and I get that. So one way of putting this is I was loading a cartridge, but I was not actually using it, and therefore I was hiding any kinds of invalid access that were being made in the range 0 to FFF. Now that I'm no longer loading that cart, I'm getting this this access at address 0 earlier. So I think this is the same bug, but like happening earlier. And I suspect what happens is that, you know, this one would pass, and then I would get similar invalid access later on in this at this address. So this is the bug that I would like to fix. To get an idea for what's going on for this bug, what I have here in, where is it, in my debugger, I have an instruction count. So right now we are, I'll just copy this, this is the instruction count. Actually, I said I had written it here. So we are at about, you know, 2,282,000 instructions in, and that's when this happens. Now, what I would like to do is implement the ability to say step with a count. So I could actually start the debugger and step up to, you know, somewhere close to here, turn on the trace, run, and then we can actually take a look at what's going on, and that will help us in general to debug these kinds of things. I don't want to actually do the full trace because it's much, much too slow. And it's also would produce a huge trace, as we've seen on previous streams. So this is what I'd like to do. And then the next thing is to add watch points. And the reason for that is because the problem I was looking at last time seemed to be that at a specific address in memory there was an invalid address that was being written, and I don't know when that got written there. So a watch point would help me detect that. So let's do this. So we've done this, talking about the bug from last stream. So now I'd like to implement this step count. All right. So just before I do that, let me check in what I've got right now. Let me commit, this change here. Okay, and yeah, I'm just gonna remove that deadline from what's in cartridge. All right, so these two changes, I'll say debugger, don't assert on invalid memory access for when what? Don't assert on invalid memory access when reading for disassembly output. I'll just put a little note here. It's okay. We want the CPU to assert fail on invalid memory access, but the debugger attempts to read addresses for information for informational purposes. So we don't want to fail. Instead, we output invalid read. Something like that. Okay. So now we can start working on this next bit. So let's do the step count. So I already have a step instruction. So I have here step, I have continue. So right now I just check if the token is step or S, it's basically the step into, and all I do right now is I say print op and execute instruction. So what do I want to do? I mean, I suppose what I want to do is stepping with some number of instructions is actually like doing a continue command, but making sure to stop after a certain number of instructions that's hit. Trying to think about how to do that cleanly. Because here it was nice and simple. I just printed the op and I executed one instruction. For continue, I do the same, and then I proceed to no longer set this break into debugger flag, which ends up entering this other loop here where we're not broken into the debugger and we just run. And the only thing that really stops us while we're running here is that we hit a breakpoint, or that the user hits Control-C. So if I hit Control-C in the debugger, basically anything that sets this mbreak into debugger true. So there's the Control-C there, the console control handler. Yeah, or like I said, if there's a breakpoint here, then it happens. I was thinking, can I make use of the breakpoint system, but I can't really because I don't know where we'll be in n instructions. So I would need to add yet another way inside this loop to check if we've executed enough instructions. And I have to be careful if we do hit Control-C or anything like that, like once we're out of this loop, we got to make sure that that counter is completely reset and not used anymore. Yeah. So I'm thinking, what can I use for that? Should I could use an STD option, because then I can see if it has been set or not. Because I would need like some kind of sentinel value. It's basically a pair. I need to know, is this feature enabled and what is the count? And I don't feel like using like a negative sentinel value or something like that. I'd rather, normally I'd like use a bool and an int, but I actually can use STD option for exactly that purpose. Like if you come here, option. Hey, it's a data snail making a debugger. Yeah, so I do have a debugger. I've had it for a little while now. So it's, and what I'm doing is I'm going to augment my step instruction so that I can pass it optionally a number of steps to take, so a number of instructions to execute. The debugger that I have is based, like it's heavily influenced by the way GDB works. Like when I was trying to think about how to write it, I was thinking like, well, you know, do I make up my own set of instructions for it? And then I thought, well, you know, GDB is a debugger that people use to debug code and assembly. So why not just use their standard way? So I'm pretty close to what GDB does. I made this little document here where I actually used this here. It's kind of like a ref. Oh, and now it's gone. Okay, well, forget that. Some kind of reference card. It was like a cheat sheet with a bunch of GDB commands, and I copied all the ones that I thought would be useful to me. So like for execution, continue, next step, finish, until. Now all the ones that are bolded are the ones I actually implemented. So yeah, I've done this, info reg, so register values, print, set breakpoints and all that. So I have all of this done. And what I want to do now is I want to be able to say step and have it step a certain number of instructions. So yeah, to do that, I'm going to use option, which is not documented here. Oh, optional, that's why. It's called optional. See, optional is cool. It's part of C++ 17, which I have access to. I have enabled the, even though it's not completely ratified, as far as I know. I think I might even be using optional somewhere. Nope, not yet. But C++, sorry, Visual Studio 2017 has implemented optional. See here, define has C++ 17. It's set to 1 for me. So I should be able to use it. So let's see how that works out. I'm going to actually have to put that in the header file here. So what I want is have breakpoints and all that. So let's try it here. Standard optional of, let's make a big type. So Data Snail says, cool, did you get that sub compare overflow bug figured out? I did, actually, a couple of episodes ago. So like, not last week, but I think the week before. I think it was in episode 5, I'd like to say. And I think I figured it out not long after you left, like maybe a half hour later. What was it again? I mean, it was a bug in my CPU implementation somewhere. Oh yeah, I remember now. It was something like, I think it was, I'd have to go back there. I mean, actually, you know what? It's probably right here in my, what was it again? It was something like I was doing the compare for the wrong register. It was like really dumb. It was like a copy paste error. Fix. That's it. I think it was this one. Is it related to AND B? Yeah, it was related to this one. It was a previous instruction that would mess up the future instruction. So if we look here at the diff, okay, so here, yeah. So you can see here, I just want to take off the fact that we can see visible white space. There we go. So the AND instruction here, I have an AND here for A, and then it was supposed to be B, but due to good old copy paste, I ended up with A here. So what was happening was, rather than ANDing a result into the B register, it was ANDing it into the A register, which was messing up the A register, which was messing other things up later on. So I think that was the one with the sub compare overflow. I think. You're asking me about sub compare overflow. Wait, what was that bug again? Is that the one we're talking about? Oh, no, 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 no. You're asking, okay, you're asking about the fact that my compare instruction was setting overflow differently from the one on that asm80.com, right? I think that's what you're asking about. So this is even earlier than that. So as far as I know, so I wrote to the author of this website. I wrote to him asking, yeah. So Data Snail says, yeah. So I wrote to this guy and asked him about it, and he wrote back and said that, you know, he said like, oh, thanks for the detailed report. He says he wrote this emulator himself, and it's likely a bug in his emulator. So that actually made me feel kind of better, because it was like, you know, it made more sense to me that what I had done was correct. But it also made me feel sad because I can't really use this emulator as a reference anymore, or at least I can't trust it completely, right? So yeah, that puts me in that kind of spot now, where when I want to compare, you know, I gotta use this emulator with a large grain of salt. So yeah. On the other hand, I've been thinking about, like, there is this other Vectrex emulator that was written that works. I think it's one of the better ones, and it does have a nice clean CPU implementation. I haven't looked at it because I'm trying not to look at other emulators when I do mine. But I was thinking about how I can, like, you know, kind of ignore the implementation, but try to integrate it into my emulator as like another CPU implementation, and do something where, like, at minimum, compile my, you know, conditionally compile my emulator with that CPU, do traces with my debugger against it, and compare that against the traces that I'd get with my own CPU and see where they differ. So, you know, that would be another way in the future for me to validate or help me discover bugs with my implementation. But I'm not there yet. So far, I'm okay. I'm fairly comfortable with the CPU implementation I have, and from what I've been seeing in the trace, we're getting quite far along. So, I mean, I could even start. I was thinking about this today. I could even start working on graphics soon. We'd already be able to, like, you know, if I do like Vectrex, I was looking at Mindstorm boot up. I don't know if this one will show it here. Like, you know, when you boot up the Vectrex, there's this like kind of dotted line that goes all around, this kind of dotted rectangle, and Vectrex is written here. And then it writes Mindstorm like this. I've seen all of this in code. I've seen the call. I've gotten the calls in the BIOS to drawing those types of lines. I've seen it try to output this kind of text to the screen. So that means if I started, and I think I'm getting this far because here there's like a score. It's really bad on this video, but I think I've gotten this far because it actually wants to show a score, I believe. I wonder if this one's any better. Like all the video. Okay, this is slightly cleaner. So yeah. And then it shows a score on the next screen. It says player 1. There's a score here. And this all takes about 10 seconds or so, and I've gotten that far with my emulator, which is running in real time. So it's kind of cool, right? So I mean, all that to say is I think I'm still a ways out before I need to start comparing against a reference emulator. So yeah, so let's do this. What do I want to call this? Num steps to execute. Something like that. Or maybe num instructions to execute, because that's actually what I'm doing. And optional works, how does it work? Right. So this, if you set it to this, it's not set. So then calling if on it will say, oh, I've got no value. If it is set, let's see here. Okay, well, this is not helpful at all. There's also null opt t. Okay, that's it. Value or returns the contained value. Returns the contained value if available. Another value otherwise. Okay, so basically this. It's not set. All right. So now I go to step. Here we go. Back in the debugger. So I know I at least want to print one and execute one instruction, and then I want to check if tokens.size is equal to 2, or at least greater than 1. What do I want to do here? So, I want to take the next token as an integer. So I have this kind of function, string to integral. I guess I'll just use that. Even though like it's mainly for addresses, it'll work even if it's a non-address. So if you want to enter a hex value, I guess that's fine. Sedated Snail says, I got to get back to work. See ya. All right, man. Thanks for hanging out. So, okay. So what do I want to do here? I want to say uint64t, so auto, or in fact, just do this. The number of instructions to execute will be equal to string to integral uint64t of tokens of 1. Just thinking about what happens if this doesn't work. I don't know. I'll worry about that later. So we convert that string to an integral and we store it into here. And we say that we don't break into the debugger, and technically I need to do this as well. So here I am copy pasting a little bit, which I don't like too much. But it is kind of like continue. Okay. So let's say I do this. So now we have a certain number of instructions to execute. And technically, I've executed 1 already. So I want to subtract 1 from it. Okay. Good. So now we go in this other loop. So we're not broken into the debugger. We want to execute as many instructions as can fit into this time slice. So while CPU cycles left is greater than 0, we do this. We check for breakpoints. That's before. We do the print op. We execute the instruction, and then we say, if this is actually set, and I don't know if I can do this. Does value return by reference? It says const uint64t ref. Yeah, I don't know. Maybe this is not what I expect. Yeah. Maybe optional is not the right thing. Because my concern here is that can I actually change this value easily. You know, maybe I'll have to do this. You know, is equal to -1, which kind of sucks. I think I have to do value -1. Why is this no good? No, I think this is fine. And like, I couldn't do dot value minus minus, right? I don't know if that, I have to check if this, so this compiles, but am I just decrementing a temporary rather than the actual value itself? Return reference to contain, oh, okay. Oh, that's good. That's really good. So I could do what I wanted. I could say if number of instructions is that and minus minus is equal to 0, just to be safe. No, actually it's UN64T. Yeah, maybe I should be careful with that. If you try to enter a negative value, it's going to be some kind of huge value. Yeah. Okay. If we reach 0, then we want to reset this. So disable it. And what? And we want to break into the debugger. In fact, like what I have here, CPU cycles left and break is what I want to do. Maybe what I'll do is this. Okay, why is this not lining up? Oh, I think I'm missing that. Yeah. So I'm going to repeat myself here twice because I have the ability to break into the debugger due to breakpoints. Otherwise, we print, we execute, and then after that, another chance to break into the debugger due to the number of instructions to execute count reaching 0. And in both cases, I need to do the same thing. I need to break out of this loop, but before that, I need to also reset my CPU cycles left. So it's not super nice. I mean, I could put this in a little lambda or something, although I can't really break out of the lambda, so. Yeah. And I can't really say this one only because I don't want to execute the instruction in the case of a breakpoint because we want to break just before. But I do want to do this decrement after the instruction because we're counting instructions executed. Unless I decrement after, but check if we reach 0 before. I could do that as well. But then I kind of separate the code. No, you know what? This is fine. I'll worry about the fact that these are copy-pasted later. At least it's all on screen, and it's easy to see what's happening here. Okay. So let's see if this actually works. Let's do a little test. Oh, I'm missing. Okay, yeah, I did mess up my parens before, didn't I? So that's that while loop. That's this if. This if. I think I just have one too many somewhere here. Yeah, that's it. Okay, let's try this out. So step 1. Wow, that did not work at all. So let's debug this. Step 1. Okay, so there's S and there's 1. Okay, so string to integral actually returned 0 because we already executed 1. Right. So, that's funny. Just trying to remember why I was worried about this and continue. First step current instruction, otherwise if we have a breakpoint, it will end up breaking immediately on it again. Right. Which also would happen for step. If we were stopped at a breakpoint and we wanted to step 10 more times, it would immediately stay on the current instruction unless we step it first. So we must step it first, just like in the case of continue. So yeah, here what I need to do is I have to say, do this, and if it's still greater than 0, if we actually do have something to do, then make sure to break into the debugger. Yeah, so it's kind of, I need to do .value here. So when we do step 1, it'll just step 1 instruction and then it's done. Okay. Let's try that. So step 1, so that worked. Step 2, that worked as well. Yeah, so step 0 doesn't work because I end up doing -1. This was my concern about using a uint. So you know what? I'm going to use an int. That's really the simplest possible fix for this. Not deal with wraparound issues and all that. Just make it an int. So if you put 0 or any negative number, nothing's going to happen because it needs to be positive. So let's try this again. Step 1 instruction, step 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Step 0, which actually ends up stepping 1 instruction, but that's okay. I mean, you asked it to step, so I'm not going to be all pedantic. I always at least step 1, because that's what step means. I'm okay with that. In any case, it's more of a error condition than anything else. Okay, that's pretty cool. So here you can really see how much slower it is with color. And then when I have color disabled and I have buffered output, it's like instantaneous. Okay, so that's pretty good. So let me see what this looks like. Handle optional number of steps parameter. And we just need to update now our help. So this is step, and then I'll put count. Step instruction, count times. There we go. So now if I type help, It says step count, step instruction count times. Beautiful. So I'm good with this implementation. I think it's still pretty relatively clear what's going on. So let's take a look at my diffs here. Let's see if it all looks kosher. Optional with an int64, num instructions to execute. Okay, that looks good. Just thinking about how anytime break into debugger is set to false, I'm going to want to reset the last time this way. So like even when I do things like until, and in multiple places I'm not actually resetting correctly. Until is another example of that. So I'm probably going to want to do this a little differently. It's kind of like making me realize that this change. Like where else am I doing this? Okay, so right now it's those three places, but in all three I would need to do this. Effectively what this is that it's a state machine problem. I need to know that I'm going from the state broken into debugger to the state running or continuing. And on that transition, I would like to reset the time. So on enter of the continuing, I would like to reset the last time. So it's right now, because I'm using just good old switch case logic or if-else logic here with this kind of implicit state machine with bools and stuff, it's really dirty and not awesome. So one way I could handle this is I can make like a local function, like break into debugger, or actually I'm broken, so continue execution or something, and like do this. If I did that, then at least I could come here and say continue execution. And then same thing here. So in the three cases where we want to continue execution, I don't know if I like that name. But yeah, I mean, I guess that's fine. Continue execution, yeah. So execute instruction, continue execution. So that gets us out of this state. So this is good enough for now. And in fact, I can do something similar here where I can say auto break into debugger. Okay, it'll align soon. And in that case, unfortunately I can't do it for the break. No, you know what? This one's okay. I'll leave this one alone. Whoops. So I did do something weird, didn't I? Okay, I don't know. Okay. So, do I like this? Yeah, I think this is good because I mean it says what we want and it takes care of, in all cases, we set this bool to false and we make sure that when we resume that we reset the frame timer. So this way we don't have to worry about the fact that we have a huge delta time when we're stopped in the debugger for a long time in all three cases. So that's good. That's actually better. So like, I can step 10, but I can also, do until this here. Until here, that does the same thing. Okay, let's go back to my diffs here. So now our diff looks a little bit different because I added this guy, calling it here, calling it inside here, and calling it there. Perfect. And here is us basically breaking out of the whole thing. Yeah, that's good. That's good. Eventually I'll probably turn this into a proper state machine, but for now it's good enough. All right, I'm happy with this, so let's commit this change. So debugger, add optional step count parameter to step instruction. Or I'll say implement optional step count parameter for step instruction. Commit and push. All right, so next on the list is probably the most interesting of the features, which is the watch points. So I'm just going to take a little break and I'll be right back in like 5 minutes. And then we can start implementing this guy. Let me turn off the music. Okay, so let's implement watch points. That's the next thing on my list. So this should be interesting. I thought a little bit about this. I even took a stab at this. And wasn't too happy with what I ended up with. So I think what I'm going to do is I'm going to start with the most straightforward implementation and then work my way out from there. So let's start with actually adding the command for the watch point. So to do that, if we take a look at how GDB does it over here, so setting watch points. So the way it, well, in GDB it's a bit more complex. You can actually implement it with expressions. And actually, if you want to set it to an address, you need to dereference the address, which is basically dereferencing which is like a C++ or C expression. I'm not going to do it exactly like that. I think it's unnecessarily complex for me. All I really care about is setting a watch point on an address. Like here, they show how in GDB setting a watch on an address like this says cannot watch constant value, but if you say cast it to an int star and dereference it, well then it'll say, okay, I'm watching that. I don't really want to do that, so yeah, I'm just going to do the basic thing. The way it works is that watch means that it's looking for writes. Then you have here rwatch, which is, so here it says watch is when it is written into by the program and its value changes. I think I'm just going to look for writes, keep it simple. rwatch is when it's read by the program, and awatch is when it will be either read or written, so like all watch, I guess that's what the A is for. And then info watch points lets us take a list, like see the list of watch points. I mean, I guess there must be also a way to delete watch points here and disable them, which they don't talk about here. Let's see. Currently, the awatch and rwatch commands can only set hardware watch points. Because accesses to data that don't change the value of the watch expression cannot be detected without examining every instruction as it's being executed, and GDB does not do that currently yet. Okay, this is just some details about hardware breakpoints. GDB automatically deletes watch points that watch local automatic variables or expressions that involve such variables when they go out of scope. Well, that's interesting. If you rerun, you will need to set all such watch points again. One way of doing that would be to set a code breakpoint at the entry to main, and when it breaks, set all watch points. Okay, let me just check. GDB disable watch point. So here, watch, continue. So that's a read. How do I disable? Info breakpoints. Oh, okay. So here, I already have info breakpoints, so I could do the same thing. I could kind of piggyback on the same thing because I have a way to number them and then to enable, disable, delete using that. And that sounds way better than... Oh, and I guess info watch just would show the same list except only list the watch points. I don't see why that would be particularly useful. I guess it's just a filter. Yeah. Okay. All right. So I mean, I'll just make sure my info breakpoints works. I don't really care that much about the info watch points. So let's do that. Okay. So I'll go near breakpoint here. There's breakpoint, and then I have the stuff to delete, enable, disable them. I'll add another case here for watch points. Watch point. I don't think W works in there. Unfortunately, my cheat sheet has been deleted. This GDB ref card. Let me just look for it like this. Oh, that's the one. I'll update my. So Stanford moved it or changed it. Okay. So let's see. Watch point. Watch. Breakpoints and watch points. So B and break. So here's watch. So yeah, they don't really have W. So yeah, you gotta do that. Show define breakpoints, show define watch points. Okay. So I'll just take this off. So what do I want to do? Yeah. So what I need to do is I need to have a way to register some kind of callback on the memory bus for when I have a watch point that gets hit. So the simplest way to do that is to actually modify my memory bus class. I don't actually want it on the memory bus, so I was thinking about ways to, have like a debugger memory bus that I would use instead of memory bus. But I'm going to start with that because that's the simplest implementation that I can do. So the idea would be that the memory bus would have some way to register callbacks for reads and writes. So something like here. So I'll say using onRead callback. So some function that accepts the actual address that's read. On write callback will be some function. I think I need to include function. Functional, I mean. That accepts, sorry, this is an address, and then this will be an address and a value. The value that's trying to be written. Okay. Okay, on read callback and on write callback. I mean, this is just my debugger that will register these for now. I will add data members for this. So there's my m underscore on read callback. And I'll only allow one because for for now, there'll be no other system that's interested in that except for my debugger. Okay, so there we go. That's registration. And then the idea would be to modify read and write to call back on this. So I'm wondering if I should first do my find device info in case there's no device, but don't think it really matters. So I'll just keep it simple. Yeah. If m on read callback. So if I have an on read callback, let's invoke it with the address. And if I have an on write callback, let's invoke it with both the address and the value I'm about to write. Okay. So like I said, this is basically the simplest implementation. I'm going to move my registration higher up. Let's leave this like this for now. So this is the simplest implementation. However, what I don't like about it is that I've now made the memory bus a non-zero cost abstraction. So if we don't use the callbacks, we're going to be paying for these conditionals. Like when we read and when we write, on every single read and write, we're always going to do this condition, which, you know, granted is probably not a big deal, although it is an STD function. So, you know, I might want to go a little bit further and like, if this actually is not well optimized, I assume it's not very long to call the operator bool on it. But anyway, this check is always being done, although it is probably currently dwarfed by the time it takes to search through my vector for the device. So it's not the end of the world. I may even be able to give the compiler a hint that this is an unlikely branch so that it will start executing the find device info while checking it to see if there is a read callback at the same time in pipeline CPUs. So that's something I could also do. But really what I would like to do, what really bothers me isn't that as much as it is the fact that this code is kind of muddying up the memory bus implementation where it's only useful to have this kind of stuff for the debugger. So what I might want to do is have a debug memory bus that wraps the memory bus or something like that. So I'll think about that for later. But for now, let's do this. Go to my debugger. In the init function, we get our memory bus here. And let's do this here. Register callbacks. Okay, the autocomplete has stopped working. This is like a bug in Visual Studio 2017 that I've noticed. At some point, autocomplete stops working, so I just got to close and reopen it. That's what I do for now. It seems to solve it temporarily. Okay, that was here. So register callbacks. And what I want to do is, for now, I'm just going to implement some lambdas for on read and on write. So for on read, when I hit this callback, oh, and I need to give it parameter. So on read is the one that gets the address. So when I get that, I want to break into the debugger. So do this, break into the debugger. And I want to also print that that's what we're doing. So I'll say here, what did I do for regular breakpoints? Breakpoint hit, so I'll do something similar. Watch point hit at %04x address. Okay. And similarly, we'll register a lambda. We'll do the lambda for the right watch point. I'll just close this. Okay. Now the formatting's a bit messed up. As soon as I hit save, the Clang format will kick in and clean this up, so I don't really care. Similarly, we want to do the same thing, except we want to say that, and I guess I can say watch point. I should say what it is, that this is a read or write. Should I just put like here maybe? Read, write, maybe. Or I can do like for read or something like that. Okay, I'll just do this for now. That's fine. So if I hit save, the Clang format does its wonderful job of formatting my code. So this should compile. Right. I should probably say what value is being written. Interestingly, when this happens, it will still end up executing the instruction. Which means that I'm probably more interested in what was the value in there before. Now, I was thinking about this because the way this works is when I set this flag to true, unlike the breakpoint, which is being checked for every instruction I check before we execute it, this kind of register callback thing will happen on the memory bus. It will happen during the execution of the instruction, and then the instruction, like, it will get this callback, but there's no way unless I do something like throw an exception or something, which maybe is a solution, like throw an exception in here and then I'll end up catching it on the outside around this like execute instruction over here. And like then I'd know, oh, okay, an exception was thrown, we didn't execute the instruction, we need to break into the debugger. So that's another option, like putting some kind of try catch. For now, I'm gonna leave it this way. The idea is this will print, will end up executing the instruction, and it will be broken into the debugger. So I'll just say here, watch point hit write value %02x. I'll just say that for now. Okay. Let's see what this looks like. All right, so I do this. Now, we're not done, right? This builds. Does this build? Yeah. Let's see if everything builds. Okay. So we have a way to register callbacks. We have a way to get the callbacks called, but actually what I did is not quite right. Right now I'm calling my callbacks for every single call, and that's not right. What we want to do is we only want to call them for specific ranges. And so calling back on every single read and write is extremely expensive. I mean, I could check in here whether those values fall into the ranges we want. That's one option, but I don't think that that's going to be very good for performance. So what I want to do instead is, for now, I'm going to let the memory bus know about which kinds of callback, like which reads and writes we're interested for the callbacks. So that means that I need to store some kind of set, or two sets anyway, a set for the read addresses and a set for the write addresses, and have a way to add, remove, and all that, these sets. Just thinking about what I want to do there. Do I want to okay, yeah. Let's include set. So a set for the on-read addresses like this, addresses, and for the on-write addresses. So now we'll just modify this to say if I have a read callback and I find the address, then we call this. And similarly, if I have a write callback and my write addresses dot find, then we do this. Okay. Now I need a way to add and remove these addresses from the list. I'd also want to be able to technically disable and enable them. Yeah, that's what I was pondering a little bit earlier, is because I have this breakpoints. What did I call it? Breakpoints? I thought I had a file for this. CPU. Oh no, sorry, debugger. Breakpoints.h. So yeah, I have this like class for wrapping breakpoints. So I'm wondering if I should try to like reuse this. Thinking a lot of things. I'm wondering now, actually, if my idea of always calling back into the debugger and doing my check in the debugger actually makes more sense. And if that's the case, then maybe in my debugger, in the same way that I have I have this like breakpoints here, I could have a data member either of type breakpoints. Yeah, I could have like two of them, but one for like read watch points and one for write watch points, and then I can treat them all kind of in the same way for enable, disable, and all that. So I have here address. So breakpoint right now is an address, whether it's enabled and whether it should be auto-deleted, which is kind of for temporary. I use that for when I do until. And maybe what breakpoint should also have is it like a hardware breakpoint. You know, is it a watch point? Is it a looking for read, write, or both? And then I can actually add them all into this one structure. Not sure. The problem is if I use one class to own all kinds of breakpoints and watch points, I need to do like special case for when I look up addresses. Like when I'm looking up for breakpoints, I'll be looking them up and have to make sure that what I get back for a normal breakpoint isn't a watch point. Is that a big deal? Do I want to pay that cost? At the same time, if it's all in one place, it's simpler because when I say info breakpoints and then my add, remove, delete, all that just works as is. So that sounds enticing. Kind of like that. I could do like, you know, I could have a type here. Something like an in class type. And it could be a, what would we call like a regular breakpoint versus a watch point? It's like a, this is like an execute versus a read versus a write versus read write. Or maybe, no, instruction would be better. This is an instruction breakpoint versus a read breakpoint versus a write. So these are really for watch points. So I could do that. Let's move this up. Type, say instruction. Although now I need to say what type I'm adding. When I add, let me explore this a little bit. Create this, set the address, set the type, set the address. Okay. So far, not so bad. We go into our debugger. And where we add to breakpoints, I'll say breakpoint type instruction. Have another one here. Maybe I'll make the type, actually, now I'm looking at it, I'm thinking, make it the first parameter. I want to add a instruction breakpoint at this address. I kind of prefer that. Okay, and I think that's the only two adds I have so far. Okay, so we go back then to the idea that we'll just always call the callback. Forget these sets. So I'll remove the lookup here. And in the debugger, when we register our callbacks, we'll say we have to check in here. If breakpoints dot get address. So this is really going to slow down significantly. I think this is going to really slow down my debugger quite a bit. I might even need to like have some extra tracking to see if there's even any watch points enabled. This is going to be very costly to always have a callback for every read and write, and to always look up if the address is in this map. So what I might want to do is only register the callbacks if we have any watch points. Otherwise, don't have these callbacks. That's probably what I'm going to have to do to make this even feasible. Okay. So if breakpoints.get yeah, I'm going to have to modify this guy as well. Like here I have to say if bp.type is not equal to instruction what? No. Okay, if it is an instruction type. It's kind of like I would like to say and here. This is why I want the C++17 if, where you do an initialization and then you can actually do things like, BP and this is exactly the perfect case, but I don't think Visual Studio supports it yet. That's evidenced by the fact that it doesn't like the comma here. But when we do have C++17 implemented in Visual Studio, I'll be able to do that kind of thing. For now I can't, so I need to do this kind of ugly code. Okay, what is it? What's the problem here? All right, I need to check if it's equal to breakpoint type instruction. So if it is an instruction breakpoint in particular, then we do this. Okay, good enough. So I'll just copy this and go back to where we were for the watch points. Okay, so if I can get a breakpoint at the incoming address, if the type is equal to type read Hey Fred. So Fred says your solution to only call back if there is a watch point seems tractable, a bit like we sometimes use conditional breakpoints, which are super slow because of debugger evaluation. Yeah, so the problem I have is a problem of like location of code. I want to use this breakpoint structure, this class that I have, and have it store all the breakpoints. Whether it's a instruction breakpoint, a read or a write breakpoint, and that lives right now in the debugger, which is what makes sense. It's where I modify and all that. The problem is that for me to have this work with the memory bus means that the memory bus has to also be aware of which addresses I'm watching or not and call back on those. So it's like this split, So what I'm thinking is right now, the most simple, straightforward thing is to have the memory bus just always call back and then do the filtering in the callback, which of course is slow for regular watch points. I'm going to see how slow we're talking here. Yeah, let's just see how slow it is. And maybe work around it by saying, well, you know, for watching for some change, that's when we pay the price. Otherwise, if there's no watch points, then we just don't register any callbacks. So if that's what you meant by your solution to only callback, if you meant like only registering callbacks, so right now I'm going to just register them on init, but this I suspect will be extremely slow. I'll be paying the cost of having the callback for every single read and write and looking up in my breakpoints whether I have watch points or not. So yeah, not super happy with this, but for now I'm just going to see where this takes me. Probably what I need to do is, like I said, I need a different abstraction. I need to have some kind of debugger memory bus that is aware of the debugger and will be able to check, do the filtering in the read and write there. Fred says, I think I misunderstood what you said earlier. Yeah, so let's just see where this goes. So if the type is a read, so actually here I can just do an early out if it's not a read. So if it is, then we break. So if not equal to read, if the type is either a read or a read-write. If that's not the case, then we get out. Actually, I'll just say if it is the case, then do this. It's a bit more straightforward. But what you just said makes sense. I hope so. I really think it's going to be super, super slow. Like unbearably slow. Okay, so for write, I think because of one character, it formats differently. See, I'm on line 100 here. Isn't that awesome? Anyway, whatever. Okay. So this, what's good about this is that now it should be trivial to register my watch points for write and for read and all that, because it's all in the same system and I don't really have to even worry about special ways of handling the info breakpoint and all that. So let's see where this goes. So Fred says, I just looked at my own data breakpoint code and it looks like this in the memory bus. If data breakpoint active and address is equal to data point. Yeah, so the thing is, see, like your memory bus is doing the check against the address. And that's what I was starting to do. But then if I do that, if I want my debugger to be able to like, list them, enable them, disable them, like, make it a sophisticated debugging environment, all of a sudden I find myself kind of duplicating the logic of managing a set of breakpoints with this metadata of whether it's enabled, disabled, and where it's at and all that in the memory bus, which sucks, right? So I do really need a kind of a hybrid solution, which I'll get to. Okay. So yeah, this is breakpoint. Now for watchpoint. So watchpoint will be very similar. So I'll even copy it. So I want to say watchpoint on some address, and this will become on a write, because that's what watchpoint does. In fact, I think what I'm going to do here is I'm going to say if it's equal to that, or if it's equal to, was it watchpoint? I think it was watch, not watchpoint. Yeah, watch. So if you say watch, yeah, in fact, this is supposed to be break. See, I never use those. I always use B, so I never tried this one. But I'm looking here. It's actually break, watch, and then this guy doesn't show it, but this is also R watch. Where did it go? Oh, it's up here. So R watch and A watch. So let's look for this. And then I'll just do a cute little looking at the first character to know which type we want. If tokens of 0 is equal to W, then we want this guy. Otherwise, if it's equal to R, then we want write. Otherwise, we want both. See how Clang formatted this code? It's cute. It actually reads quite well. This kind of cascaded thing that it does. What is it that doesn't like here? Oh yeah, sorry, the type. It's not the type is the first parameter, and then the address is the second. So there, in one step, I was able to do watch, R watch, and A watch. Okay, enable, disable, and all that will work. I do want info break to list whether it's a watch point or not, or at least let me list the type it is. So here, when I do info break and it lists the breakpoints, we'll add an extra thing here. So right now we're showing if it's enabled or disabled at the end. We're also coloring it, saying here index address enabled and disabled. Okay, I'll put it actually in between. %s type. I need like the type to string type of thing, but anyway. You know what? I'll do it in here, in breakpoint. It's too bad I can't add functions to the type. It's that classic namespace enum is sometimes nicer than enum class. Namespace enum is going to be around for a while, I feel, says Fred. Yeah. Yeah. Well, I mean, it's okay. I'll just do this here. Breakpoint, : type to string. Kind of works. Not super happy with it, but it's okay. I like enum class. I like not having, like, I like that, you know, you don't have to do : type like we do with namespace enum. And yeah, I don't know. It's a first class citizen, so that's cool. You can, but it's not perfect. Okay, so instruction, read, return, read, write, and case rewrite will return read write. Oh yeah, and I have to put type : I wonder if it's going to complain, the compiler, about missing return type here. Probably. So here we'll say string bp type. So we get it as a string. Oh yeah, this has to be static. It's not a namespace. So let's see what that looks like. Not all control paths return a value. Okay. Info break. Let's say I set a breakpoint at 0. Info break. So it says instruction. Let's set a watch on same address. Info break. Huh. Yeah. Guess I can't have both. That's okay. So break, let's say on 0. Watch 1, R watch 2, and A watch 3. Info break. Okay, yeah, so I thought would happen. Just need to put sizes for my strings in the printf. But this allows me to say, like, disable 1, and then you see it's even red, just cute with the coloring. And actually, I don't even think I'm respecting the enable disable stuff. And I was thinking about that, like, things that would be nice for my breakpoints is checking, like, it would be nice to have some helpers when I get breakpoints to say, like, oh, just get it for me if it's actually enabled, type of thing. Fred says, that is super cool, you are hacking the matrix. Yeah, with the coloring. Yeah, I think it would be nice to have, like, some helper functions. Underscore breakpoint get. Is that it? Oh, breakpoints, yeah. Or not. Okay, yeah, I'm checking if it's enabled. I'm also checking if it's an auto delete. This is really a special case for using a breakpoint, an instruction breakpoint that I run until somewhere. Here I'm checking if it's a read or a read write, but I should also check if it's enabled. Yeah, so I might put some helper functions, like instead of doing it like this, I'll have like, get if valid or get enabled, maybe pass a type, so I don't repeat my logic here. But for now, let's do this. If I'm enabled, and I gotta wrap my logical OR in here. So if I'm enabled and it's either this or this type, okay. Oh, now they actually line up better. Okay, so let's see if this works. I need to just find something that writes. So here, I have a store here of A to D000. So let's quit and let's try writing, let's put a watch on D000. So I added breakpoint at there. I might want to say added watch points if I do this. It's probably nicer, since I'm actually writing that string here. Let's try it again. So watch that and continue. And there we go. Watch point hit at D000. Write value 1. Info reg. That's interesting. Yeah, so basically this is a store D instruction, which actually performs 2 writes. It's going to write the first byte of D and then the second byte of D. And the first byte of D is actually A and the second byte is B. And so what it's saying is that it broke because on the first write, which is at D000, it was writing 1. And it already did it, which is, which is fine. So that seems to work. And if I continue, there's yet another write where we write value 3, which should be an A as well. Yeah. Okay, now if I say info break and I disable this breakpoint, disable 0, we should be able to continue. And if I say set the dude register to FF, okay, and if I take off trace, usually this runs for about 10 seconds before I get and there we have it. This must be the invalid cartridge read at address 0. And it is. So it looks like it's working. Just do a few more tests. I'll do like I'll look for a read access instead of a write. Okay, so any kind of load here. So a load from actually memory. So there we go. I'm loading from C82C here. So let's put a R watch on C82C. Okay, continue. Boom. Watch point hit at C82C. Right value 0. That's not right. Let's look at my callbacks. Did I call the wrong callback? That's possible. Let's go to the memory bus. So all right, let's put a breakpoint in here and see what's going on. So R watch. Oh, actually, it's R watch the problem. It set it to be a write. So the problem is not here. The problem is in where R watch is being set. So it's this logic here. Oh yeah, there it is. That's better. So W is this. So that's a normal write watch. If it's R, it's a read. Otherwise, it's A, which is a read-write. Okay. So I can take off these. All right, R watch, C82C, and continue. Interesting. So this time I got a watch point hit at C82C, read. And then it shows, yeah, then it executed the instruction. Why? Why did it print it this way? I guess it really depends on when the read occurs. Oh, right. I suspect that the reason this is happening here is because of my debugger reading from the memory bus. Yeah. Because my debugger reads from the memory bus in order to display this, and this happens, the disassembling of the instruction happens before the CPU executes it. In the middle of disassembling it, it goes and reads C82C, and then that causes the watch point to be hit. It prints this. Then after that, it finishes disassembling, outputs the disassembled version, and then executes the instruction. So that's why that happens. Now, I don't think I want my watch points to be hit when the disassembler is running, so I need to have some kind of hack to kind of like override, like disable temporarily the callbacks for the disassembly part. Okay, so let's do that. So we'll have some kind of like master switch on this. So on read write callbacks enabled. I'll just say callbacks enabled. So set that to true, and then we'll have a bool. So if enabled, register callbacks, and I'll say set callbacks enabled. Like that. In my debugger, when I go to disassemble, which is part of this print op instruction here, I say memory bus set callbacks enabled false. Doesn't like it because it's const. Okay, I'll actually just work around that for now by doing it in this print op here. Say take the memory bus, set callbacks enabled to false, and then set them back on true here. And I'll just put a little comment. Don't stop on watch points when disassembling. All right, so I think I lost my address that I was watching. What was it? See something. I should rewatch my stream recording to see what it was. I'll just find another one. So set the dude register to FF. Let's see here. I think it was this one, CBE4. So let's try that again. Oh, it was a read actually, wasn't it? Not a write. So I'm not sure this will. Oh, there we go. Okay, so I set a read watch point on CBE4. I ran and it said watch point hit at CBE4. Why? It's not showing me that instruction. Okay, CBE4. Now I will put breakpoints in here. It's a read that I care about, so I'll put it here. Okay, and I'm not hitting it this time. Oh, it's because I didn't set it properly. Okay, set dude equals to FF, rwatch, CBE4, continue. Okay, so here we are. Oh, so it's actually part of the return to subroutine. Oh, okay. Really? Because it's actually popping that value off the stack? That's cool. Let me see if I can reason about that. CBE4. So that means that that's basically right. It's the stack pointer. There we go. Because we're loading S here to CBEA. So when it reads at CBE4, which is the stack basically goes backwards when we push to it. So when I made this jump subroutine, it wrote to CBE4, and then when we return from subroutine, it ends up reading there. So that makes sense. So I should choose another. Yeah, it's going to keep doing that. So there's another return to subroutine. So yeah, I'm not going to watch addresses on the stack because that's just annoying. So I'll say I delete that. So deleted breakpoint. So I'll just continue and I'll pick somewhere where we're reading from memory. So these are load. Actually, I could have picked any of these loads. Load B. I need a load from memory. Here's one. Load A from F11D. So rwatch this guy. And continue. And there we go. So watch point hit at F11D. This, like what I'm writing here, watch point hit at this address. It's not super clear, but I'm supposed to put a $sign here. Now what about a read-write? What's going to happen there is, yeah, it's a read-write, and it'll tell me if it was a read or a write that occurred. Yeah, so that's good. So Fred says, Commander of the Most Excellent Order of the British Empire, CBE. I don't even know what that is. So let's do a RA watch. That's the last one I want to test. So it would be fun to watch something that gets both written to and read from. Oh, actually, if I use the stack, that would be perfect, right? So what I was doing before with the stack value, that'll be written to when we jump subroutine, and it'll be read from when we return from subroutine. So that would be a good example. So let's try that. It's like CB, what was it again? It's EA, it was E4, I think it was, yeah. So if I do an A watch on that and continue, see I get a watch point when we do branch to subroutine, and we get a watch point hit when we do a return from subroutine, and there's the write and there's the read. Write value F1, oh, yeah. $sign here. And is it F1 that gets written? Yes. Yeah, because it's going to write F164, or maybe actually F166, and I only show the first value that gets written because that's the one byte that's written here, and then there's another byte that gets written before. So Fred says it's part of the system of chivalry in Britain. Okay. Because of the CBE, right? is pretty awesome. So it looks like it's working. I'm pretty happy with that. I mean, actually, it didn't seem to have affected performance all that much. Fred says, it is awesome. Thanks, man. Yeah, I'm surprised. I'm surprised it's not worse, the performance, because I'm actually calling this for every single read and write. So, I mean, I'm sure it's going to show up. Right now, it's not showing up because I'm not doing anything, but eventually it will, and I'll have to optimize it. But I'm not going to optimize it just yet, because right now it's pretty straightforward. Even like the changes to the memory bus are relatively straightforward. It's like just this stuff, actually just, yeah, the changes here are inside here. Read and write has these callback calls. We can register them. We can have this global switch on whether they're enabled or not. And all I have is these three data members to handle that. So not too bad. I will just put a little to-do in here. Move this callback stuff out of here. Perhaps in some debugger memory bus class. Okay. Cool. So yeah, so I've got watchpoints implemented, which will allow me to debug the issue. However, it's almost midnight, so yeah, I had these two more items on my agenda, which will have to wait till next time. So I'll just get this stuff committed. Yeah, okay. Let me look over my changes here. So struct breakpoint, I added this enum type, I added this little function here to convert the type to a string. Okay. Breakpoint add, you now must provide a type when you add, and it'll store it. Just take a look first at memory bus here. Functional and set were added. Actually, I don't need set anymore, so remove that. Functional I need for these std functions, because I'm storing these callbacks. Okay. Read became this read. Yeah. Right. Okay, this looks good. Debugger. I think I'm going to open Beyond Compare for this one. Okay, I don't know where that white space came from. Register callbacks. So there's a read callback and the write callback. In run, I make sure to disable them before disassembling or printing the operation. Okay. Drop down. Okay, so until we'll add a auto deletion instruction breakpoint. Oh yeah, one thing I didn't do was alignment for info break. I wanted to do that, so that's trivial. I'll just put here what's long enough. Let's see here. Breakpoint. Okay, it's not showing up in my in here because I just need to regenerate my my CMake. Let me do that. Is that the right one? Build 2017 CMake. Come back in here, reload solution. Now we should see the breakpoint file in here. There we go. So, longest string is this guy. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's give this guy 16. So break on 0, watch 1, R watch 2, and A watch 3, info break. Okay, that's good. Actually, these should be left aligned. I think it's minus. Let's try that again. And then I do a tab. Do I really need to do a tab? I don't. So I'll make this just slightly longer then. Do that. Watch 1. That looks better. R watch 2 and A watch 3. See, all nice and lined up. So now if I do like disable 2, that's what it looks like. And then I can say delete 2, and that removes it from the list. We're all happy. Okay, perfect. So reload. Let's continue looking at my diff, break, B, instruction. So this is not lining up. There we go. Watch, R watch, A watch. Okay. And then so this is a bit more. All right, the formatting for info break to show the type. And I needed to make sure that the type was instruction when doing a breakpoint, a proper breakpoint. Okay. Very nice. So let's get this committed. Implement or add watchpoint support. Watch, R watch, and A watch. Commit and push. Okay, so that means I'm at a point where for today's agenda, I ended up doing everything up until here. So next time, I might do this turbo mode thing. just to make it go faster. And then we'll be able to finally debug this weird access that's happening. We'll try to figure out what is writing to memory that's causing it to read that address. So yeah, that will be for next time, which it's most likely going to be on Wednesday, in a couple of days. So yeah, thanks for hanging out, guys. Thanks, Fred. Talk to you later. Yeah, and I'll see you guys next time.